first introduce myself. My name is Alexandra Phillip. I currently attend Embry-Riddle Aeronautical University, located in Daytona Beach, Florida, majoring in aerospace engineering with a minor in flight test and simulation. Embry-Riddle is one of the top aviation schools in the country, especially if you would like to pursue a career as a pilot. Every student in an aviation curriculum benefits from hands-on learning and maintained aircraft equipped with glass cockpits, labs that replicate the nation's airspace, state-of-the-art maintenance and avionics repair facilities, and unrivaled aviation simulation centers. Students who have the best in aviation education choose the world's best aviation and aerospace university. Today, I'll be giving an introduction into aviation and flight training. So if any of you choose to pursue a career as a pilot, you first have to start from the beginning towards accomplishments of a private pilot certificate. And you begin to achieve the certificate by taking flight lessons. You can begin taking lessons at any time, but you must hold a student pilot certificate solo in the airplane, as required in the FARs, which stand for Federal Aviation Regulations. To be eligible for a student pilot certificate, you must be at least 16 years of age, be able to read, speak, write, and understand the English language, and hold at least a third-class medical certificate. To attain a medical certificate, you must pass a physical exam administered by an FAA-authorized aviation medical examiner. You can request to be issued a combination medical certificate and student pilot certificate at the same time of your examination. Student pilot certificates also may be issued by FAA inspectors or FAA design pilot examiners. In addition to the student pilot requirements, to be eligible for a private pilot certificate, you must be at least 17 years of age, complete specific training and flight time requirements, described in the FARs, pass a knowledge test, and complete a practical test. Performing pilot operations and executing maneuvers in the airplane. The FARs require that you have received instruction in specific flight operations and maneuvers, as well as ground instruction in certain knowledge areas. In addition, there are minimum flight hour requirements that must be completed to apply for a private pilot certificate. According to FAR Part 61, you must have completed at least 40 hours of flight time, consisting of at least 20 hours of dual instruction, and at least 10 hours of solo flight. If you are enrolled at an approved by FAR Part 141, you're required to have at least 35 hours of flight time, including 20 hours of dual instruction and at least 5 hours of solo flight. You should remember that these are minimum hour requirements. The average student with no prior flying experience requires approximately 65 to 75 hours to meet proficiency standards necessary to pass the practical test and operate safely as a private pilot. The private pilot training program can generally be divided into 3 phases: pre-solo, cross-country, and practical test preparation. Each phase includes both flight and ground training. During the pre-solo phase, your training progresses from the initial flight lesson with your instructor to flight. Your flight training as pre-flight inspection of the airplane, taxiing, emergency takeoffs, as well as maneuvers away from the airport areas, climbs, descents. During ground lessons, you learn how to obtain weather information, examine characteristics of the make and model of the aircraft in which you will solo, and review pertinent regulations. During the cross-country phase, you learn how to plan flights to airports outside of the local area. You will gain skill in using aeronautical charts, procuring and interpreting weather information, calculating airplane performance, and determining the weight and balance condition of your airplane. The final phase of your training includes a review of all the flight maneuvers rounds throughout the training program prior to your practical test, which pilots generally as the check. Instructor endorses your logbook to indicate that you have completed the required training to perform each pilot operation safely as a private pilot. Although airplanes are designed for a variety of purposes, the basic components of most airplanes are essentially the same. Once the practical aspects of building an airworthy craft are resolved, what ultimately becomes the final model is largely a matter of the original design objectives and aesthetics. In a sense, then, airplane design is a combination of art and science. Although the artistic possibilities are virtually limitless, the relatively inflexible scientific requirements for manned flight dictate that most airplane structures include, at a minimum, a fuselage, wings, an empennage, landing gear, and a power plant. The fuselage houses the cabin and/or cockpit, which contains seats for the occupants and the controls for the airplane. In addition, the fuselage may also provide room for cargo and attachment points with other major airplane components. When air flows around the wings of an airplane, it generates a force called lift that helps the airplane fly. Wings are contoured to take maximum advantage of this force and may be attached at the top, middle, or lower portion of the fuselage. These designs are referred to as high, mid, and low. The number of wings can also vary. Airplanes with a single set of wings are referred to as monoplanes, while those with two sets are called biplanes. Attached to the rear or trailing edges of the wings are two types of control surfaces referred to as ailerons and flaps. Ailerons extend from the midpoint of each wing outward to the tip and move in opposite directions to create aerodynamic forces that cause the airplane to turn. Flaps extend outward from the fuselage to the midpoint of each wing. The flaps are normally flush with the wing surface during cruising flight. When extended, the flaps move simultaneously downward to increase the lifting force of the wing for takeoff and landing. The empennage typically consists of a vertical stabilizer, the rudder, the horizontal stabilizer, and the elevator. These surfaces act like the feathers on an arrow to steady the airplane, helping maintain a straight path through the air. The rudder is attached to the back of the vertical stabilizer and can be used to move the nose of the airplane left or right. The elevator is attached to the back of the horizontal stabilizer. You can use it to up and down desired altitude or height. The landing gear observes landing, loads, and supports the airplane on the ground. Typically, the landing gear consists of three wheels. Two main wheels, one located on each side of the fuselage, and a third wheel positioned either at the front of the or rear of the plane. Landing gear employing a rear-mounted wheel is called a conventional landing gear. Airplanes equipped with conventional landing gears are sometimes referred to as tailwheel airplanes. Landing gear can also be classified as either fixed or retractable. Fixed gear always remains extended and has the advantage of simplicity combined with low cost. Retractable gear is designed to streamline the airplane by allowing the landing gear to be stowed inside the structure during cruising flight. The increased weight and cost of retractable gear systems normally limits their use to high-performance aircraft. In small airplanes, the power plant includes both the engine and the Propeller. The primary function of the engine is to provide the power to turn the propeller. Accessories mounted on or connected to the engine generated electric power create a vacuum source for some flight instruments. And in most single-engine airplanes provide a source of heat for the pilot and passengers. A firewall, which is located between the engine compartment and the cockpit, not only protects the occupants, but also serves as a mounting. The engine compartment is enclosed by a cowling. Aside from this line, the nose of the airplane, the cowling helps cool the engine by ducting air around the cylinders. The propeller mounted on the front of the engine translates the rotating force of the engine into a forward-acting force called thrust that helps move the plane through the air. Although the number of blades on a propeller can vary, most general aviation training airplanes use a two-blade propeller. Engines in widespread use today can be divided into two categories: reciprocating and turbine. Most large passenger-carrying airplanes use the form of the turbine engines, which is relatively costly but extremely powerful. The large power output of the turbine engine is not required in general aviation training airplanes. A form of the more economical but still very reliable reciprocating engine is used. In typical reciprocating airplane engines, the continuous energy creating process is referred to as the four-stroke operating cycle. The steps in the cycle are the intake of fuel or air mixture, the compression by the piston, the ignition and expansion of the gas, and the venting of the burning gases. The intake process is when the piston moves away from the cylinder head on the intake stroke. The intake valve opens and the fuel or air mixture is drawn into the combustion chamber. For the compression process, as the piston moves back towards the fuel or air mixture is compressed. Power plug is ignited, rapidly expanding gases from the controlled burning of the fuel or air mixture drives the piston, providing the power that. And finally, the exhaust process stroke expels the burning gases from the chamber through the opened exhaust valve. Pitot-static instruments rely on air pressure to measure speed and altitude. The airspeed indicator, altimeter, and vertical speed indicator all use surrounding or static air pressure. Pitot pressure, which is only used by the airspeed indicator, is a combination of the static pressure plus pressure generated as aircraft moves through the air. Pitot-static instruments use pressure-sensitive devices to convert pressure supplied by the pitot-static system to the cockpit. Pitot pressure, also called impact or ram air pressure, is supplied by the pitot tube or head. The pitot tube is usually mounted on the wing or on the nose section. The opening is exposed to the relative wind. This arrangement allows ram air pressure to enter the pitot tube before it is affected by the airplane structure. Since the pitot tube opening faces forward, an increase in speed increases ram air pressure. Static pressure enters static through a static port, which is normally mounted on the side of the fuselage in an area relatively undisturbed air. The airspeed indicator is the only instrument operating using both pitot and static pressure. The speed of the air is determined by comparing ram air pressure with static air pressure. The greater the differential, the greater the speed. The airspeed indicator is divided into color-coded arcs that define speed ranges for different phases of flight. The upper and lower limits of the colored arc correspond to system airspeed limitations called V speeds. The altimeter senses pressure changes and displays altitude in feet. It usually has 3 pointers or hands to indicate the altitude. The longest pointer shows hundreds of feet. The middle-sized pointer indicates thousands of feet. And the shortest pointer shows tens of thousands of feet. The changes in air pressure directly affects the accuracy of the altitude readout. The altimeter is equipped with an adjustable barometric scale. The vertical speed indicator, which sometimes is called the vertical velocity indicator, uses static pressure to display or descend in feet per minute as the airplane climbs or descends. The VSI determines the vertical speed by measuring how fast the ambient air pressure is increasing or decreasing. The primary gyroscopic instruments used on most trained airplanes include the trim coordinator, attitude indicator, and heading indicator or compass. Gyroscopic instruments operation is based on 2 fundamental concepts that apply to gyroscopes: rigidity in space and precession. The trim coordinator is a relatively modern version of the early turn and slip indicator, many of which are still in use today. Both types of indicators provide an indication of turn direction and quality, as well as a backup source of bank information in the event of attitude indicator failure. The primary difference between the two is the display of turn or roll information. The turn and slip indicator uses a pointer called a turn needle, and the turn coordinator employs a miniature airplane. Both indicators use a ball in the tube with an inclinometer to provide information regarding to the quality of the turn. The attitude indicator senses roll There uses an artificial horizon and miniature airplanes to depict the position of the airplane, especially used to horizon visibility or darkness. The heading indicator, also called a directional gyro, senses airplane movement and displays heading based on a 360-degree azimuth, with the final 0 omitted. In other words, 6 indicates 60 degrees, 21 indicates 210 degrees, and so on. When properly set, it is your primary source of heading information. Heading indicators in most training airplanes are referred to as free gyros. This means they have no automatic north-seeking system built into them for the heading indicator to display the correct heading. You must align it with the magnetic compass before flight. However, precession can cause the selected heading to drift from the set value. For this reason, you must regularly align the indicator with the magnetic compass. The magnetic compass is a self-contained unit that does not require electrical or suction power. To determine direction, the compass uses a simple bar magnet with 2 poles. The bar magnet in the compass is mounted so it can pivot freely and align itself automatically with the Earth's magnetic field. During flight, the 4 forces acting on the airplane are lift, weight, thrust, and drag. Lift is force created by the effect of airflow as it passes over and under the wing. The airplane is typically supported in flight by lift. Weight is caused by the downward pull of gravity. Thrust is the forward force that propels the airplane through the air. It varies with the amount of input. Drag is the backward or retarding force that limits the speed of the airplane. In unaccelerated flight, the 4 forces are in equilibrium. Unaccelerated flight means that the airplane is maintaining a constant speed. and is neither accelerating nor decelerating. To efficiently manage the large amount of traffic that traverses the sky each day, the atmosphere above the United States is divided into several sectors or classes. In each airspace class, specific rules apply. For example, there are VFF, which stands for Visual Flight Rule, weather minimums that you must maintain in each airspace class. In some areas, you're required to communicate with ATC and comply with pilot certification aircraft equipment requirements. In addition to the primary classes, the airspace over the United States includes special use and other Air Force areas where certain restrictions apply or specific ATC services are provided. Controlled airspace is a general term that covers 5 of the 6 classes of airspace. Class A, B, C, D, E. While operating in controlled airspace, you are subject to certain operating rules as well as pilot qualification and aircraft equipment requirements. Class G airspace is referred to as a controlled airspace. There is no airspace designation for Class F in the United States. Normally, ATC does not accept control of traffic in uncontrolled or Class G airspace. You are not required to communicate with ATC when operating in Class G airspace unless a temporary control tower has been established. In early consideration, all airspace was uncontrolled. Today, due to the need to coordinate a large amount of traffic, a major portion of airspace that covers the contiguous but controlled, and the amount of uncontrolled has continued to. The majority of your flying time will probably be spent in controlled airspace designated as Class E airspace. There are no communication requirements to operate within Class E airspace, but you can request traffic advisory services that ATC provides on a workload permitted basis. In Class E airspace, you cannot fly when the weather is below VFR minimums unless you are instrument rated IFR, but plan and receive a clearance from ATC. An airport that has an operating control tower but does not provide radar services, as in Class B or C, is surrounded by Class D airspace. The control tower provides sequencing and traffic advisories to VFR aircraft operating into and out of the airport, and IFR traffic separation. It was established two-way radio communication with the tower prior to entering Class D airspace and maintain radio contact during all operations to, from, or on that airport. As a general rule, you should avoid Class D airspace except to take off or land at an airport within the area. Factors considering in designated controlled airspace include safety, users' needs, and the volume of air traffic. Because of these considerations, many busy airports are surrounded by Class C airspace. Within a Class C area, ATC provides radar service to all IFR and VFR aircraft, and participation in the service is mandatory. An outer area normally extends out to 20 nautical miles from the primary airport, where radar service is available but not mandatory. Class C areas usually have similar dimensions from one location to another, although some may be modified to fit unique aspects of a particular airport's location. At some of the country's major airports, Class B airspace has been established to separate all arriving and departing traffic. While each Class B area usually is designated for a major terminal, it typically serves several airports in the area. A Class B area has different levels of airspace that are portrayed as a series of interconnected circular patterns around the airport. You may notice it looks something like an upside down wedding cake. Each Class B area is individually designed to serve the needs of the particular airport that it surrounds. Terrain, the amount and flow of traffic, and the location of other airports all influence each design. Generally, you will find that Class B airspace surrounds the busiest airports in the world. The airspace extending from 18,000 feet mean sea level up to and including flight level 600 is defined as Class A airspace. It covers the majority of the contiguous states and Alaska, as well as the area extended 12 nautical miles out from the U.S. coast. To operate with Class A airspace, you must be instrument rated. In addition, your aircraft must be transponder equipped, operated under an IFR flight plan, and controlled directly by ATC. Because of the overall increase in speed of the aircraft operating in Class A airspace and the corresponding increase of closure rates between the aircraft, VFR flight is not allowed. Jet routes are designed to serve aircraft operations from the floor of Class A airspace up to and including flight level 450. Communication radios in general aviation aircraft use a portion of the very high frequency or VHF range, which includes the frequencies between 118 megahertz and 135.975 megahertz. Communication radios are classified according to the number of channels they were designed to accommodate. A 360 channel radio uses 50 kilohertz spacing between channels such as 118.05, 118.10, 118.15, 118.20. 720 channel radio doubles the frequency available by using 25 kilohertz or 0.025 megahertz spacing such as 118.025, 1.18.050, 118.075, and 118. Since communication radios usually combine transmitter and receiver, they are called transceivers. When you're using the radio, it is important to speak in a professional manner that ensures that others understand the message you are trying to convey. Slang, CB jargon, and incorrect radio procedures can compromise your safety and the safety of others. Radio transmissions should be brief as possible to help avoid frequency congestion. Before you depress the microphone button, think of what you will say and listen for a few moments to make sure that someone else is not already talking or waiting for a response. You should state who you are, where you are, and what type of service you are requesting. Any other information may be excessive, especially in busy terminal areas. It would be difficult for pilots to speak all the languages that could be involved in an international flight. Therefore, the English language is recommended by the International Civil Aviation Organization for international air or ground communication. In countries where English is not the official language, ICAO member states have agreed to make English available upon request. ICAO also has adopted a phonetic alphabet to be used in radio transmission. When you identify your aircraft during initial contact with ATC or other facilities, you will use the phonetic alphabet as a routine measure. And when you transmit or receive messages over the radio, each number is spoken the same way you're used to saying it. With the exception of the number 9, it is spoken as Niner to distinguish it from the German word Nein, which means no. To reduce confusion, certain sets of numbers are spoken as individual digits. When you state radio, not this point, but the decimal is dropped when you state an altimeter setting. To operate within a large terminal area with radar services, you need to be familiar with a number of ATC functions that are necessary to coordinate departure and arrivals. The following scenario covers the various ATC functions and the normal order that you would use them. So, if you are at controlled airports, you must receive permission from ATC to taxi to the active runway and subsequently be cleared to take off. You can expect more complex departure procedures at larger airports due to heavier traffic and more ATC services. So before contacting ground control, you usually listen to the ATIS recording, which includes current airport information and such as the altimeter setting and active runway. Then the clearance delivery facility is established at busy airports, mainly for ATC to relay IFR clearances to departing IFR traffic. However, when the ATIS message so indicates, you should contact clearance delivery prior to taxiing. You should include your IN number and aircraft type. I'll specify that you are EFR and have listened to the current A. Finally, identify your destination or direction. This allows departure controllers to improve traffic coordination. Clearance delivery may provide detailed you to contact ground control. Ground control is an ATC function for directing the movement of aircraft and other vehicles on the airport surface before ground control to taxi to the active runway. At busy airports, you may be instructed to wait in the holding area near the runway. At unfamiliar airports, you can request a progressive taxi, which means the controller will provide you with precise taxi instructions or will direct you in stages as you proceed along the taxi route. And then after completing the before takeoff checklist as a departure runway, you normally switch to the control tower frequency for takeoff clearance. When you receive takeoff clearance, make a final check for traffic before you taxi onto the runway. You may be asked to line up and wait. This means that you have positioned yourself on the runway for takeoff while waiting for another aircraft to clear the runway. Usually, you can expect to be cleared for takeoff after the other aircraft is cleared. After takeoff, contact departure control and a controller will advise if you are in radar contact. From radar, your aircraft has been radar identified and flight following will be provided. If you receive flight following, the controller is observing the progress of your aircraft while you provide your own navigation. Approach control is the ATC function that provides separation and sequencing of inbound aircraft and traffic advisories or safety alerts when necessary. Approach control frequencies are published on sectional charts and broadcasted over ATIS. At large terminals, expect different frequencies for approach control depending on your arrival sector. On initial contact, ATC routinely provides you with wind, runway, and altimeter information unless you indicate that you have received the ATIS or you use the phrase have numbers. The phrase have numbers means you have received only wind, runway, and altimeter information, but does not indicate that you have listened to ATIS. Weight and balance. Almost every aspect of performance is influenced by the weight of the aircraft and its contents. For example, compared to a properly loaded airplane, an overweight airplane has longer takeoff run, higher takeoff speed, reduced angle and rate of climb, reduced cruise speed, shorter range, higher stalling speed, and longer landing roll. Loading an aircraft too heavily can dangerously decrease its performance and increase the risk of structural damage. And if you encounter turbulence or make a hard landing, or even when maneuvering, as you might expect, a severely overloaded airplane will not fall at all. In addition to checking weight, you need to know that the aircraft is balanced within approved limits. It's not just a matter of how much you put into the airplane, but where you put it. You can check the balance condition of an airplane by locating its center of gravity, which is an imaginary point where the aircraft would balance if suspended. The location of this point is critical to the airplane's stability and elevator effectiveness. Improper balance of the airplane's load can result in serious control problems. You can avoid these problems by taking the time to determine the location of the center of gravity before each flight and then making sure it is within the limits provided by the manufacturer. The center of gravity limits are the forward and aft center of gravity locations within which the aircraft must be operated at a given point. Also called the center of gravity envelope or range, the center of gravity limits are established by the manufacturer. Many aircraft are certificated in more than one category and will have different center of gravity limits depending on the category in which the airplane is operated. If the center of gravity is located within these limits, the airplane can be flown safely. If it is located outside these limits, you will need to rearrange fuel, passengers, or cargo in order to move the center of gravity within acceptable limits. It's also important to maintain this distribution of weight during flight. Any movement of passengers or cargo will change the location of center of gravity. Center of gravity limits usually are specified in inches from a reference datum. This is an imaginary vertical plane from which all horizontal distances are measured for balance purposes. Common locations are the nose of the airplane, the engine firewall, the leading edge of the wing, or even somewhere in space ahead of the airplane. The location of the datum is established by the manufacturer and is defined in the POH or in the airplane's weight and balance paper. Basic empty weight includes the weight of the standard airplane, optional equipment, and stable, unusable fuel and full operating fluids, including full engine oil. Unusable fuel is a small amount of fuel in the tanks that cannot be safely used in flight or drained on the ground. Older airplanes might use the term license empty weight, which is similar to basic empty weight, except that it does not include full engine oil. Instead, it only counts the weight of undrainable oil. You can obtain basic empty weight by simply adding the weighted oil to the license empty weight. Ramp weight is the term used to describe the airplane loaded for flight prior to engine start. Subtracting the fuel burned during the engine start, run up, and taxi yields the takeoff weight. This is the weight of the airplane just before you release the brakes to begin the takeoff roll. Landing weight is the takeoff weight minus the fuel burning en route. To determine an airplane's useful load, either prior to engine start or at takeoff, you must subtract the basic empty weight from ramp weight or takeoff weight, respectively. The useful load includes the weight of the flight crew and usable fuel, as well as any passengers, baggage, and cargo. Payload is the term used for the weight of only passengers, baggage, and cargo. Adding the weight of the flight crew and usable fuel to the payload is another way to determine useful load. Some PLHs may refer to total weight or gross weight, which are general terms used to describe the weight of the airplane and everything carried in it. The name for a distance from the datum is arm. On airplanes, the distances are generally measured in inches, and by tradition, after the datum are positive numbers or the datum are negative. Stabilization is another term for the arm. A weight on the end of the arm creates moment. A moment is a measurement of the tendency of the weight to cause rotation at the fulcrum. An arm is simply a length. A moment is the length multiplied by a weight. When the weight is in pounds and the arm in inches multiplied together, the resulting moment is expressed in pound inches. The position of the field gravity of the airplane is measurement of the arm determines gravity. Gravity is an object or group of all the parts divided by the so sometimes during weight and balance competitions, you find that the body field falls outside of cosmos and gravity location over and over, but there's an easier way, and that would be the following formulas in the pictures shown. Okay, now the flight planning process. Whether you are traveling across the continent or simply across the route to an enjoyable and safe flight begins with the flight planning process. This pattern of pre-flight activities requires that you put into practice all of the skills you require throughout your training. As you gain experience, you may refine and customize your planning procedures. However, this is just to show you a general process. It should be seen similar. So first we would have the flight overview, in which you would have a discussion with your flight instructor in regards to the stops at what airports you will go to, as each leg of the flight will emphasize a particular method of navigation, so such as VOR, pilotage, or dead reckoning. And then you would also be doing a weather briefing into how would you expect the weather to be by the time you are flying. And then the next process is developing the route. And with this, you would review the WAC chart. And after reviewing the chart, you would gather other materials and resources necessary to refine your computer navigation logs, flight plan, IMs, and Southwest Airport are facilities. And after all this, you would also check the terrain and obstruction heights and select a preliminary altitude for each leg of your flight, considering FAR requirements and VFR cruising altitudes. And of course, the actual altitude that you will be flying will be determined by the winds aloft and clouds covered on the day of the flight. And then next in the process would be the pre-flight weather briefing, in which you would have to wait at least an hour and a half before departure to obtain a pre-flight weather briefing. And so you would call the FSS to request a standard briefing, and to make sure that you have your route data and a blank weather log handy. After identifying yourself as a student pilot flying VFR, you'll be able to provide the briefer with the type and registration number of your airplane and your approximate cruising altitude and estimated time of departure. And then the next step in the process is navigation log. And with this, you would finish completing the navigation log by completing wind direction and magnetic heading, the time, fuel, and distance to climb, performance figures, ground speed, estimated time on route, estimated time on arrival, and the total fuel requirements. You also calculate takeoff distance and landing roll for the en route and destination air. And then after determining the fuel requirements, you perform a weight and balance calculation. And so without passengers and load baggage, the airplane is well within weight and center of weight limits. And the next step is the flight plan. And so upon completion of navigation logs, you review the results with your flight instructor. And if neither you or your flight instructor finds anything that will cause you to change, delay, or cancel the flight, then you will be able to proceed to fill out your flight plan. And then the final step is the pre-flight inspection, in which you determine if you're fit to fly. So you proceed to check the aircraft logbooks to ensure that the plane has been maintained in accordance with the FARs. The owner or operator is primarily responsible for maintaining the aircraft in airworthy condition, since a satisfactory review indicates that the airworthiness certificate for the airplane is still valid. You continue to the airplane to complete your pre-flight inspection. And then during the pre-flight inspection, you would check the aircraft components in the logical sequence using the appropriate checklist. And then you examine the fuel samples to check for contamination and verify that the airplane has been serviced with the correct grade and amount of fuel for the flight. And you must be careful to complete the aircraft pre-flight inspection for the first flight of the day by using a thorough and systematic means recommended by the manufacturer. So thank you again for watching this presentation and getting a glimpse into the possibility of pursuing a career in aviation as a pilot or within any other field of aviation. But if you ever want to learn more or gain more interest in the aviation, as it is an expensive field, there are many organizations such as OBAP, AOPA, and Women in Aviation that provide scholarships as well as programs for students to get involved in aviation early. And so definitely check out these organizations, and you may also look into getting Jepson private pilot books if you're interested in already looking for or studying for becoming a private pilot.